A-level topic of thermodynamics. Thermo meaning heat, dynamics meaning movement. So this is a branch of physical chemistry that deals with heat, energy, temperature and physical properties of matter. Here we're going to look at the terms enthalpy and entropy in this video. We're going to start with looking at some key words. Now these are the key words we need to know the definitions of, as the exam papers will often ask us to define the various terms. First we are looking at enthalpy change. So whenever we are looking at the term enthalpy, our units of enthalpy are kilojoules per mole. So to calculate enthalpy, often we do our amount of energy in kilojoules divided by the number of moles required to make that particular energy change. So this is linked with our Q equals mc delta T. If you're unsure of how to use that equation, please see the alternative video on the required practical for Q equals mc delta T. So the term enthalpy change is the amount of heat energy transferred during a chemical reaction at a constant pressure. An enthalpy change of reaction can either be positive or negative. This tells us whether energy has been given to the surroundings or taken in from the surroundings. If our enthalpy change is a positive value, this refers to an endothermic reaction where energy is being taken in from the surroundings, and a negative enthalpy is an exothermic process, meaning energy has been required or released from the surroundings. So exothermic, energy released from the surroundings; endothermic, energy absorbed from the surroundings. Next we look at enthalpy of formation. The definition is the enthalpy change when 1 mole of compound is formed from its constituent elements in their standard states at standard conditions. If we are ever asked to define the standard enthalpy of, the standard refers to standard conditions, and that's 298 Kelvin and 100 kilopascals. So let's look at an example of an equation that represents enthalpy of formation. So let's imagine we are forming 1 mole of sodium chloride, our compound. The elements required are sodium and chlorine. Sodium is a solid at room temperature, chlorine is diatomic, Cl2, and it's a gas. So we would need half Cl2 in order to have 1 mole of our compound. Now the enthalpy change of formation of an element or a molecule in that standard condition, for example chlorine or sodium, is 0, because by definition they are not a compound, so we are not forming them. Ionization enthalpy, often referred to as ionization energy, is the amount of energy required to remove an electron from a gaseous atom to form 1 mole of gaseous ions. Now we could have the first ionization enthalpy or the second ionization enthalpy. This is just a general definition. Now because energy is required to do this process, to remove an electron, to overcome the attraction from the electron and the nucleus, this is requiring energy, therefore the process is always endothermic. It requires energy for it to happen, so we always expect the ionization enthalpy to be a positive value. If we were to look at an example of the first ionization enthalpy of sodium. So to remove an electron from gaseous atoms to form 1 mole of gaseous ions. So we are gaseous atoms and we are removing an electron to form gaseous ions. First ionization enthalpy refers to 1 electron being removed. If we were to look at the second ionization enthalpy of, let's say, magnesium, we already have removed that first electron. So then we are removing that second electron to form magnesium 2+. Next definition is enthalpy of atomization. This is the enthalpy change when 1 mole of gaseous atoms is formed from its element under standard conditions. The reason why we need to know this term is for when we begin to look at Born-Haber cycles. Because as we can see in the ionization enthalpy, we started with sodium in its gaseous atom form. Sodium is typically a solid at room temperature. So in order to look at the data for ionization enthalpy, we first need to atomize our sodium. So because we are forming, so 1 mole of gaseous atoms is formed, atomization is always endothermic. Because what we are doing is overcoming or breaking any bonds between the atoms. For example, we've got 1 mole of sodium as its element in its standard conditions to form 1 mole of gaseous sodium atoms. So we have to overcome or break the bonds between the individual atoms or bonds. Therefore, endothermic and atomization is always positive. Bond enthalpy, sometimes known as bond energy or bond dissociation enthalpy. This is the amount of energy required. So if we require energy for something to happen, we have to absorb energy, therefore endothermic. So our bond enthalpy will always be positive. And it's the energy required to break 1 mole of specific covalent bond in the gas phase. So for example, if we have 1 mole of HH in our H2, what we are doing there is breaking 1 mole of the bond between H and H atoms. Bond forming, where we would also look at bond energy or bond enthalpy, to form a bond or to make a bond, that releases the same amount of energy that's required to break it. But to make a bond, you are releasing energy, so the making of bonds is an exothermic process, so we would tend to see negative values for that. Next up is lattice energy, often known as lattice enthalpy. The enthalpy change when 1 mole of ionic crystal is formed from its gaseous ions. So because it is a formation and we are looking at this lattice dissociation enthalpy, it's exothermic because we are forming, we are combining and bringing together ions. As previously mentioned, thinking about when we are making bonds, energy is released. So this is exothermic, so we would always see a negative value. So if we wanted to think, we've got sodium ions, gaseous, plus chloride ions, gaseous, to form 1 mole of ionic crystal sodium chloride. That is a representation of the lattice enthalpy for our sodium chloride. Now, lattice enthalpy and the value of lattice enthalpy will depend on a number of different factors. The factors it depends on will be the ionic radius and the charge of the ion. Now, you can't determine lattice enthalpy or lattice energy from an experiment. It can't be directly determined. So often we see Born-Haber cycles used to calculate lattice enthalpy, where we use other data and an indirect route to calculate lattice enthalpy. Now, a large negative value of our lattice enthalpy, meaning it's highly exothermic. This suggests our ionic compound is more stable than the gaseous ions that it started with. This is typically due to the strong electrostatic attraction found within the lattice, keeping those ions close together and therefore more stable, so requiring more energy to overcome those forces. So the more exothermic your value, i.e. the more negative your value, the more stable your ionic compound and the stronger the ionic bonds are. Because the ionic bonds are the attraction between the positive and negative ions. Electron affinity. The electron affinity is the energy change when 1 mole of electrons is gained by 1 mole of gaseous atoms to form 1 mole of gaseous ions. So let's look at our electron affinity, our first electron affinity for chlorine. So we have 1 mole of chlorine atoms in the gaseous state, adding 1 mole of electrons to form Cl- ions in the gaseous state. Now this is a negative value. The first electron affinity is always negative, because when we are gaining that electron, the electron is attracted to that nucleus, so energy is released. However, often with second electron affinities, for example, if we have the O- ion and we are gaining an electron to form the oxide O2- ion in its gaseous state. This is an endothermic process, meaning this second electron affinity is positive. Being endothermic means it requires energy to happen. So why might we need to require energy to gain another electron? Well, we are trying to add an electron to something that is already negative. Therefore, there is a large force of repulsion. So we have to overcome that force of repulsion to gain that second electron. Enthalpy of solution. This is the enthalpy change when 1 mole of ionic substance dissolves in sufficient water to form an infinitely dilute solution. Sufficient water meaning enough water to dissolve. As an equation, this can be represented as, let's take an ionic compound such as KCl. We use the state symbol AQ to show the sufficient water. Goes to KCl, which is aqueous. Or we could represent this as KCl solid, sufficient water, because what will happen when we dissolve an ionic substance in water is it will break apart the lattice. Therefore, those individual ions are broken up and are free to move within that solution. Enthalpy of hydration is the enthalpy change when 1 mole of a gaseous ion dissolves in sufficient water to form an infinitely dilute solution. Let's look at an example. Mg2 plus, gaseous, so we're in the gaseous ion, dissolves in sufficient water, so we use that state symbol AQ to show that, forms Mg2 plus AQ. Hydration enthalpies are the measure of the energy that is released when there is an attraction formed between the ions and the water molecules. Meaning hydration enthalpies are always exothermic, having a negative value due to that energy being released when there is an attraction. For example, if we have our water molecule where there is some slight dipole charges due to the electronegativity of the oxygen, and we have our ionic solid, there is an interaction between the partially positive hydrogen and the negative ion. That's also to say there is an attraction between the partially negative oxygen and your positive ion in the lattice. This interaction weakens the electrostatic attraction in the lattice, therefore breaking up the lattice. So let's look at another way to calculate lattice enthalpy using hydration and solution data. A reminder of our definitions that lattice enthalpy is when we form an ionic compound from its gaseous ions. So we are setting up an equation from the gaseous ions to the ionic compound. The gaseous ions, when they are dissolved in sufficient amount of water to form an infinitely dilute solution, is the definition of enthalpy of hydration when we are going to our aqueous ions. Enthalpy of solution is when we are dissolving our ionic compound, our lattice, in sufficient water to dissolve to form our aqueous ions. So similar to a Hess cycle, if for example we wanted to know the enthalpy of hydration, we can go via an alternative route to find the enthalpy of hydration using lattice and solution data. The enthalpy of hydration would equal the enthalpy, the lattice enthalpy, plus the enthalpy of solution. Now let's imagine we wanted to find the lattice enthalpy. And we can't find lattice enthalpy, so we go via an alternative route. So our lattice enthalpy, we are going in the same direction as the enthalpy of the hydration, and then we're in the opposite direction of our solution, so minus enthalpy of solution. So just to note at this point, our lattice enthalpy for our potassium chloride, we look for the sum of the hydration enthalpies for each of our ions. So that is our K plus the enthalpy of the hydration of the Cl minus ion, and then we minus that from the enthalpy of solution. And all the necessary data will be given to you. On to entropy. Now, why do we need to know about entropy? Entropy explains to us why endothermic reactions that typically have a very high activation energy actually occur. For an endothermic reaction, we would really need a lot of energy to start this chemical reaction, and the products are less stable than the reactants. Now, the majority of chemical reactions we see are actually exothermic. So they just go by themselves. Not a lot of energy is required to actually make them happen. So why is it that endothermic reactions occur at all? And the explanation from this is due to entropy. Now, the units of entropy are joules per Kelvin per mole. They tend to be of smaller magnitude than enthalpy data and calculations, which is why we use the joule scale to note entropy values. Now, what is entropy? Entropy really is a measurement of chaos. The more chaotic a system, the higher the entropy. Instead of the term chaos, we use disorder. If a system is highly ordered, there is low entropy. When we have a higher magnitude of disorder, therefore a system is less ordered, more chaos, there is a higher entropy. Looking at the possible arrangement of atoms or molecules will give us an idea about entropy. In a solid, there is more order. There's a regular arrangement of our atoms or particles. They are in a regular pattern, therefore highly ordered, so less disorder, meaning solids have lower entropies. Whereas gases, there is a high measurement of disorder. It's chaotic. These gas molecules can move in random directions at random speeds, therefore having a higher entropy. So it's not just solids, liquids or gases that give us an idea of disorder, it's also the number of molecules. The more molecules we have in a particular system, the greater the possible arrangement. There's lots of different orders that these can go into. There's more combinations that these molecules can move around in. Therefore, much higher entropy, more chaos. The greater number of molecules will give us a higher entropy. Now, an increase in entropy, a higher entropy, means that we are more energetically stable. For example, the reaction between calcium carbonate forming calcium oxide and carbon dioxide. So this is the thermal decomposition of calcium carbonate. we note calcium carbonate is a solid and we have got one of our compound. We've got one lot of calcium carbonate. Our products are both a mixture of a solid and a gas. So because we are producing a gas, there is a higher entropy of the products. We are also producing 2 molecules of products versus one of our reactants. Therefore, in the products, there's a higher entropy. So both of these things explain to us that the entropy is increasing. And with increasing entropy, we have a more energetically stable product. Therefore, those products are more energetically favourable, as the energy of the system is more spread out. So when our entropy is increasing, the energy is more spread out, they've got more areas to spread themselves out. This means that it's more stable. We can calculate entropy changes. Now, in our data book, entropy values have been calculated for every atom, molecule, compound. So we can calculate the entropy of a system. Now, what do we mean by the entropy of the system? A system are the molecules that are reacting. Anything on the outside of the system, which could be the solvent, the air in the surroundings, or indeed the reaction vessel itself, in this case our beaker, these are classed as the surroundings. Together is the total entropy. So to calculate the entropy change of a system, we look for the sum. So this symbol here refers to the sum of the entropy of the products minus the entropy of the reactants. So if we wanted to calculate the entropy change, the overall entropy change of the reaction between nitrogen and hydrogen to produce ammonia, we would look for the entropy of the product. So that is the entropy of 2 lots of NH3. The stoichiometry, the number of moles, is important. We'd minus that from the sum of the entropy of the reactants. So that's the entropy of N2 plus the entropy of 3 lots of H2. Now, depending on your exam board, so hopefully you will know whether this is on your exam board or not, based on whether you have heard of it before. The entropy of the surroundings can be calculated. So remember, the surroundings is anything on the outside of the system that are not the molecules reacting themselves. And to calculate that, we do the negative of the overall enthalpy change of your reaction over T. Just bear in mind, if you are ever asked to calculate entropy of surroundings, or indeed later when we come on to Gibbs, where we are using entropy, which is joules per Kelvin per mole, and we use enthalpy, kilojoules per mole, and temperature, which is Kelvin, you will need to convert either your enthalpy into joules per mole or your entropy into kilojoules per mole. So typically, if we were going to convert our enthalpy into joules per mole, we would multiply that number by 1000. Those units need to be consistent. So we can understand whether we have a reaction that is feasible or not. So feasibility is, will that reaction go? Feasibility depends on the enthalpy and the entropy. Now the size, or whether they are positive or negative, will give us different values for our Gibbs free energy. Now Gibbs free energy is anything that is left over, so any energy that is not talking about the enthalpy or the entropy within the system or the entropy within the surroundings. Anything that is left over after carrying out the reaction is what Gibbs free energy is. So the enthalpy change is the difference between the energy you put in to break the chemical bonds and the energy when you make those bonds that's released. And the entropy change is the cost of carrying out the reaction itself, the system and the surroundings. Gibbs free energy is anything left over. Now the Gibbs equation is as follows. So the change in Gibbs energy, delta G, the units, kilojoules per mole, is the enthalpy of our reaction minus T, where T is the temperature in Kelvin, times the delta S of the system. So again, our units of enthalpy typically are kilojoules per mole, our temperature is Kelvin, and our entropy is joules per mole per Kelvin. So we do need to convert typically the enthalpy into joules per mole by multiplying by 1000, or going the other way, because our units, because then we would need to convert our units of Gibbs. So our Gibbs units are kilojoules per mole, so we are going to convert our entropy of system into joules per mole by dividing by 1000. Now when we calculate Gibbs energy using data that is typically given to you, we will either end up with positive or negative values of Gibbs. And this will tell us whether our reaction is feasible or not. So when delta G is negative, the reaction is feasible and is likely to occur. When Gibbs is positive, the reaction is not feasible and unlikely to occur. So feasible tends to be used to describe reactions which are energetically favourable, so the reactions should go. So being energetically favourable links us back to the entropy and both enthalpy. And spontaneous tends to be used to describe whether the reactions go on their own or whether we need to supply it with some higher temperature, for example, to supply it with a greater activation energy. Now we can manipulate the Gibbs equation to calculate temperatures at which reactions are feasible. So because for a reaction to be feasible, our Gibbs needs to be negative. So if we say that Gibbs is 0, so 0 or below negative, our reaction is feasible. Now we are trying to work out the T, the temperature at which the reaction becomes feasible. So we're going to add T delta S over, and we get delta H. So T equals delta H over delta S of the system. Once again, you've got to bear in mind those units, so be careful that the units are consistent. Occasionally we can see graphs of our temperature versus Gibbs, and we get a straight line graph which, if we think about our GCSE maths, links us to y equals mx plus c. So I'm just switching these around because we have an mx and we have a c left on its own. So what we're saying is our c, which is the y-intercept, is our delta H, our enthalpy change. Gibbs is plotted on the y-axis and our temperature is plotted on the x-axis, which means when we calculate the gradient, that is the negative of the entropy of the system. And where our straight line graph crosses our x-axis, so that is going to be where the Gibbs free energy is 0. So referring back to this, when Gibbs is 0, we can work out the temperature that reaction becomes feasible. We can see that by the intercept of the x-axis. So let's look at some typical reactions to determine whether they are feasible or not. So we have our enthalpy change. So we're going to look whether our enthalpy change is negative or whether our enthalpy change is positive. So when our enthalpy change is negative, we have ourselves an exothermic reaction. When our enthalpy change is positive, we have an endothermic reaction. Now, depending on the reaction and your value for your entropy of the system, this may be a positive or a negative value, depending on if your reaction becomes more or less ordered. So let's say we are going to look at a positive of the system and a negative, and then a positive and a negative. So we're using the different combinations here. So as the temperature increases, what is going to happen? So for an exothermic reaction with a positive entropy of system, it makes delta G more negative. Why? Delta G equals delta H minus T delta S. So if our delta H is negative, and then we are looking at a positive value here. So as temperature increases, we are going to end up with a larger positive number. So you are going to be doing a negative number minus a large positive number. So when you're doing a negative number, take away a large positive number, you are going to end up with a negative number. Therefore, will our reaction be feasible? Yes, because Gibbs is negative. Now, what about if we've got an exothermic reaction? So we're going to manipulate our Gibbs equation again. So we are going to have another negative value for delta H, and now we're going to have a temperature multiplied by a negative number. So we're doing a negative number minus a negative number. So what we end up with is, let's just make up some numbers. If you've got minus 100 and you're minusing minus 50. So what we've got is T delta S is actually less than our delta H. I should say more than because of the signs. So that makes delta H negative. But what about if we have a larger value for T delta S? By larger value, I mean a more negative value. So a more negative value, so it's going to be much less than our delta H. Then we would end up with a Gibbs that is positive. So only sometimes, it depends. So T delta S has got to be greater than our delta H, so it will usually be spontaneous. So again, our Gibbs, if we've got delta H minus T delta S, and now we're looking at our endothermic reaction, so we're going to have a positive enthalpy minus T times an entropy that is positive. So a positive number minus a positive number. if we're increasing the temperature, it makes T delta S much larger than delta H. So what would happen is, if this number here is much larger than our delta H, then we would get a Gibbs that is negative. So therefore, at lower temperatures, this number here is going to be lower than our delta H. Therefore, Gibbs is positive and will not be feasible. So yes, but only above a certain temperature, typically at higher temperatures. And then finally, we look at the manipulation of Gibbs once more. And we are looking at an endothermic reaction, so a positive delta H. And we are going to be minusing a T times by a negative number. So what happens here is we've got a positive number, and if we, are increasing temperature, we just get a larger negative number. A positive minus minus, that's going to give us a Gibbs of positive. So therefore not feasible. So in this circumstance, delta G is always positive, so it is never going to be spontaneous or feasible.